Today we'll be talking about the redesign and analysis of a waffle maker. First is the product introduction. Here our focus is the difference between the primary and the secondary customers. The primary customers being that of restaurants and hotels, and the secondary being of that of families and small cafes. Here's the CAD explosion of the product with their labeled parts listed on the right.
This is the product analysis of the waffle maker. For the fast diagram, this shows the key functions of our waffle maker. And this is the function component mapping matrix showing what function each part associates with.
Now moving on to the product family design. In our product functional differentiation table, you can see that for the secondary customer, they are not concerned with flipping the cook surface or the ease of cleaning, given that they don't care about the quality of the waffle as much as a restaurant would, or their product is not being used as frequently, thus cleaning is not as important. This leads us to a differentiation between the platforms and the modules. Most notably, the modules reduce the rotational components, the number of brackets, number of handles, and which stand is being used. A photo of these changes is shown here, where in the secondary customer, you can see a lack of a handle and a more robust frame and the lack of rotational components. Now it can be seen in these interfaces where there's a detachable handle for modularity. A stand works with both platform waffle makers, and the pipe connectors have the same profile. One is just solid and one allows for rotation.
This is the assembly sequences for our waffle maker for it before and then after when we redesigned it to make the assembly more efficient. This is the function component mapping matrix highlighting which parts we decided to redesign for the manual DfM. Based on this quad chart, the housing and the stand tubes are the most important for redesign because they both have high functional importance and the housing is also high manufacturing cost. So this shows the DFA manual parts that we chose to redesign being the housing and the stand tubes. Before the redesign, the total assembly time was 222 seconds and the efficiency was about 19%. For the housing, we redesigned it to reduce the part count, add features for easy insertion, and we also provided locating features. And for the stand tubes, we redesigned it to eliminate the stand tubes, some of the parts. We increased part symmetry, and we also enabled a snap fit. And this shows the redesigned DFA manual table. The efficiency increased to 21.76%, the part count decreased to 35, and the total time for assembly also decreased to about 193 seconds.
Next, we looked at the design for automated assembly. We decided to select the grid and cover subassembly consisting of 5 parts: the grid cover, heater, grids, handle, and top bracket. We then looked at the function component mapping matrix for the parts of the subassembly. We noticed that there were overlapping functions for the grid cover, the handle, and the top bracket. These overlapping functions give us the opportunity for part consolidation to reduce assembly cost. We also looked at the DFA quad chart and determined all subassembly parts have high assembly costs. Here is the before design of the grid and covered subassembly. We calculated the total automated assembly cost to come out to be 53.6 cents per part. We then modified 3 parts of the subassembly using many DFA techniques. We first removed the top bracket, which reduced part counts. We also replaced the screws with snap fit joints, which eliminated fasteners and facilitated feature orientation and insertion. Lastly, we consolidated the handle into one part with the grid cover, which helped reduce the part count. Overall, these changes had no significant effect on the product's function. Additionally, these modifications would increase the grid cover manufacturing costs, but eliminate the cost for the top bracket and handle. The redesign of the grid and cover subassembly was determined to have an automated assembly cost of 40.3 cents per part, which reduced the assembly costs by 13 cents from the original design.
The first part selected for redesign was the grid cover, which was consolidated with the handle and introduced a snap fit in the design for automatic assembly. A tolerance of 24 thou was selected, which is the standard tolerance of a die casting of a part of this size. As seen here, the key dimensions are locations of the holes to fit the connecting bracket, as well as the snap fit joints to ensure proper alignment of the grid with the waffle grid, or the grid cover with the waffle grid. The important dimensions were derived from the need for the grid cover to prevent burns, meaning it needed to interface properly with the hot waffle grid. The grid cover is designed to be made out of aluminum with a certain shape, mass, section thickness, tolerance, and batch size. From this, it was determined that die casting, powder methods, and machining were capable of production. Die casting was chosen as the recommended process. The second part selected for redesign was the housing, which consolidated the part into one and introduced a flange for easy assembly. A tolerance of 10 thou was selected, which is the standard tolerance of a sheet metal pressing part of this size. As seen here, the key dimensions are locations of the holes to fit the cover and switch. These important dimensions were selected because the housing needs to prevent burns, thus all components must seal against it properly. The housing is designed to be made out of aluminum with a certain shape, mass, section thickness, tolerance, and batch size. From this, it was determined that sheet metal forming, machining are capable of production. Sheet forming was chosen as the recommended process for this part.
We then conducted the cost calculations of the top grid cover. As previously mentioned, we selected die casting for this part. We used the shown equation to calculate the total cost per part, which was about $4.76. Then we looked at modifications that we could do to ease manufacturing from both the Lecture and DfM Pro. We decided to make this one plane so that the cavity would be more simple. We eliminated the fasteners as previously mentioned, so this removed holes that we would have poles for, and we inserted draft angles so it would be easier to remove from the cavity. Once we modified this, we redid the cost calculations in the same way and got a resulting $4.64 per part. This had an 11 cents reduction per part, which is a total impact of $9,370 saved per the $85,000 parts. This had relatively no impact on the function and saved us a lot of money.
Next, we looked at the electrical casing. Here we used the Hub's cost pricing website and extrapolated in order to get our price for one unit at our quantity of $85,000. Here you can see it came out to be $23.41. We then used DfM Pro to alter our electrical casing and use their suggestions. Some of the suggestions came up as the ratio of the bend radius to the thickness of the sheet, as well as the angle of the sheet, made it really hard to manufacture. So you can see our original casing showed on the left, and then our new modified casing showed on the right. Here we optimized the bend radius according to the DfM Pro standards, as well as optimized the thickness, as well as created it flat so there was no angles for ease of manufacturability. Again, we did our Hub's cost pricing and extrapolated for our desired quantity at 85,000 units. Here it came out to about $19. So overall, the Hub's extrapolation would save us around $4.42 per unit. And then we performed the calculations using the formulas shown in lecture and got around $1.72 in this way, savings per unit. Again, there's little impact on the function as we just designed for the manufacturer, and the function is keeping all the electronics and parts safe inside remains the same.
Our product system service design includes a maintenance and repair plan offered to customers, as well as a website where they can customize their own waffle mix and get it delivered, a forum for recipe ideas, and customer service, and a place for users to submit their feedback. This impacts the customer experience because it's less expensive to maintain the product rather than replace it, and it encourages and improves engagement with the waffle maker. This impacts the environment by reducing the waste and resulting in a longer product lifetime. Here you can see the original design and our final redesign on the right. The overall benefits would be an improved efficiency and decreased part count for a DFA manual, a cost reduction of 13.36 cents for a DFA auto, and then reduced costs and improved manufacturing efficiency for DFM. Our critiques would be improved ease of manufacturing, and cons would be no rotation feature and a simple design. And in the future, we would like to increase the DFA manual efficiency to be over 1.48% and implement a more versatile base structure. And thanks for watching.